Today's lesson, we're going to talk about buffered solutions. So I want to go over just a real quick objective preview so that you can see what we will be covering this week and possibly into next week, but I'd really like to get through this information this week. So we're going to be talking about a buffered solution, which will be describing the composition of a buffer, like what is it made of, explain how it works, and how to maintain a constant pH with a buffer, or a pretty constant pH, explain how to prepare a buffer with a specific pH, calculate the pH of a buffering system, both before and after adding both H plus and OH negative. And then if you notice, we'll also be talking about acid-base titrations, where we're going to choose the proper indicator for an acid-base titration. We'll be looking at the pH of strong acid, strong base, weak acid, strong base, strong acid, and weak base during the titration of those species. And then we're going to interpret titration curves for those species. So looking at an introduction of buffers, equilibrium is established within mixtures of acids and bases. Buffers are made up of weak acids and their conjugates, or a weak base and its conjugate acid. So you've got to have a weak acid and its conjugate, or a weak base and its conjugate, in order to make a buffer system, okay? And then those are the other things that we'll be looking at as we're going through this process. Buffers are highly resistant to changes in pH that are caused by the addition of a strong acid or a strong base. So a strong acid would be H plus, or a strong base OH minus. The pH is close to the pKa of the weak acids used. What does that mean? pKa is simply the negative log of the Ka value. So it's actually really easy to determine what kind of buffering system I would want by just simply looking at a table of Ka values, and you can take the negative log of that and you'll end up with the buffered system. Okay, it consists of a weak acid and its conjugate base, or a weak base and its conjugate acid. It reacts to neutralize a strong acid or strong base. So if you notice the equation that we see here, we can have the weak acid plus the OH minus will produce the conjugate in water, or the conjugate piece that's present plus the hydrogen ion will make some more HB. Okay, so we're going to be looking at how to produce a buffer system, the pH of a buffer system, what appropriate buffer system would be used to maintain a desired pH, and we're going to calculate the small change in pH that occurs on the addition of acid or base and something called buffering capacity. So if we look at our Ka expression that we've been writing over and over and over again, this is a typical weak acid reaction, and then we have our Ka expression that we would write with that. We would assume that our acid concentration is approximately equal to the initial concentration of our acid. I'm going to have to plug my computer up here real quickly before I forget it and it goes dead on this video. And then that the conjugate base concentration is approximately equal to the initial conjugate base concentration. And so we're going to ignore the little bit that's associated, or we also call that terminology hydrolyzes with water. So we could look at this, let me go back, we could look at this, trying to get that out of the way so we could see that very last thing down there. Okay, so down here at the bottom, we could look at our reaction in terms of moles of HB and moles of B minus, rather than looking at molarity. Because if you think about it, the number of liters could cancel out, because you're going to have the same concentrate, you're going to have the same number of liters in each one. Okay. If we look at that previous equation and we take the negative log of both sides, then we end up with something called, the final form is the Henderson-Hasselbalch equation. So taking the negative log combines your original Ka expression with the pH equation. So you could end up with this equation, and this is on your equation sheet, by the way, just to simply find pH. So it's a real quick and easy way to come up with a pH of a buffered system. Okay, we will use that from time to time, but we'll also use, it's the same math, it's just how do you want to look at your math? Do you want to look at this in a real quick algorithmic way, or do you want to work with it in a step-by-step manner? Okay, so example 1, we have a buffer is prepared by dissolving 1 mole of lactic acid in and 1 mole of sodium acetate in enough water to make 550 milliliters of solution. Now this time they're wanting us to calculate the hydrogen ion concentration and the pH for this. So we could use the Henderson-Hasselbalch equation if we wanted to, although I feel like that we might want to take this a little one step at a time. So let's go over and let me show you this written down. Okay, so here's what I've got. We're looking for this. We don't know pH. Those are the 2 things that we're trying to find. Now what we do know is that we have 1 mole of the acid. I'm just going to use HA for our acid. And we have 1 mole of the conjugate, which they called Na-lact, but let's just call it A-. That's our conjugate of our weak acid. And so if we use the rearranged Ka expression, we have H plus is equal to Ka times the moles of the acid over the moles of the conjugate, okay? Or as I like to call this, the acid over the C base. Now, cool thing about this is you can put either moles or molarity in here, okay? And I think it's really easy to do moles simply because you don't have to worry about the volume. It makes your problem a lot faster to work. So I forgot to write down the Ka for that particular acid, so I'm going to have to scroll back over and grab that. Okay, so the Ka value is 1.4 times 10 to the negative 4th. Okay, and so I'm just going to plug this information in. I've got 1 mole of the HA over 1 mole. And so I noticed that 1 divided by 1 is still 1. So H plus is equal to 1.4 times 10 to the negative 4th, which is actually really cool. If your buffer situation, your buffer solution is a 1-to-1 mole ratio, then the H plus is just equal to the Ka value, okay? So 1.4 times 10 to the negative 4th. And if I want to find the pH of that, I'm going to plug that into my negative log. It's 1.4 times 10 to the negative 4th is equal to pH. And when I plug it in, let's do that real quickly. Okay, and I get 3.85 for the pH. And so that is the pH of our buffered solution. Now, notice that in this situation, the number of moles of HA and A minus are the same. So H plus is equal to our Ka value. If you take the negative log of H plus, that gives you pH. If you take the negative log of your Ka, that gives you pKa. And so the best buffer system has the best buffering capacity is going to have a concentration of a 1-to-1 mole ratio of acid to its conjugate base. That's going to be your best buffering system. All right. And so you can determine if you have a buffer for a specific pH by taking the negative log of the Ka value. Let me show you what I'm talking about with that. Okay, so if I look at this this table of Ka values here, and I've already taken the negative log of the Ka, which is called the pKa, and let's say in this question I want to make a buffer that has a pH of 9. So I'm going to come over here and look and find which one of these has a pKa that's closest to 9, and it looks like it would be the ammonium ion would have a pH that's closest to 9. So our desired pH is 9. Notice by taking the negative log of the Ka value, I get 9.25. So that's going to be our best buffer system for a pH of 9. If I wanted a pH, say, of 6, okay, I'm looking over here at my pKas, and the carbonic acid is going to give me a pKa of 6.36. So that would be the best buffering system to use if I wanted to have a desired pH of 6. So how do you form a buffer? Well, here's an example of how you can form a buffer. You can mix a weak acid and its conjugate base, like we did in the previous example, or we can partially neutralize a weak acid or weak base with a strong species. So in this next problem, we see that we have H plus NH3, and I'm going to go ahead and write that down on my paper so we can talk about that and we can see how that works. And that H plus just comes from a strong acid. So we're starting off with 0.1 moles of your HCl, and that's where we get the H pluses from. And we have 0.2 moles of NH3. So this is how we can make a buffer system without having both of these. Like, it's like, oh, I've got some ammonia, but I don't have any ammonium chloride, or I don't have any ammonium nitrate. So I need to make a buffer out of this. I do have some hydrochloric acid, so let's try making a buffer out of that. And in fact, that's what we can do. Let me show you how you can end up with both pieces. Now, notice that your amount of hydrogen ions is 1/2 the amount of NH3. So you're going to use up all of this. This is all gone, okay? Initially, excuse me, we'll start out with 0 of the NH4. Sorry about that. Oh. And we'll have, we're going to subtract 0.1 moles of this. So we'll have 0.1 moles of the NH3 left. I'm going to have to pause my video here so I can go get it. Okay, so we have used up 0.1 moles of our base. We'll have 0.1 moles left. And if your initial concentration of NH4 is 0 and your change is 0.1, if you're subtracting on that side, you add on this side. And so for NH4, when you reach the end of your reaction, you'll have 0.1 moles of NH4. Look, you have weak base and its conjugate. You have a buffered system. Just remember that a weak base and its conjugate acid make a buffer. A weak acid and its conjugate base make a buffer. You have to have both pieces in order to have a buffered system, okay? So that's your second way of making a buffer. You can either just put the stuff in where you have a weak acid and its conjugate, or you can use the weak species mixed with a strong other species. Like if this is a weak base, I would mix it with a strong acid. If this was a weak acid, I would mix it with a strong base. Okay, now I'm going to kind of skip through some of this, and I want to look at what's happening whenever we add a strong acid or a strong base to our buffered system. Okay, so let's go back and first of all, let me write down what we're going to be adding. So in A, we're going to be adding a 0.1 mole solution of hydrochloric acid, and then in B, we're going to be adding a 0.1 mole solution of sodium hydroxide, which is a strong base, okay? And everything else is still the same, just like we had before. So we're still working with our buffered solution. We have 1 mole of our weak acid and 1 mole of our conjugate. So we've got this situation where you've got H plus is equal to Ka times the moles of our weak acid over the moles of our conjugate. So I'm going to go ahead and set that up down here. At this, H plus is equal to the Ka of the moles of the acid divided by the conjugate base. Now the only thing that's different with this is we're adding some HCl to this. And I don't care about the Cl because it doesn't do anything from water. It's coming from a strong acid. So the only thing that's going to change the pH in this process is the hydrogen ion. So I'm adding some hydrogen ions to this species. And which part of this is going to eat up the hydrogen ion invader? Is it going to be the acid or is it going to be the base? What's going to neutralize the hydrogen ion? Well, okay, since this is an acid, the base part is going to be the part that interacts with it. So A minus, and we're going to end up with HA. Okay, now remember that you had some A minus to begin with. We had 1 mole of that, and originally we had 1 mole of this, and I'm adding 0.1 mole of the H plus. So initial, change, end. I'm using E for end rather than equilibrium. We're using up minus 0.1 minus 0.1 plus 0.1. So when we finish this neutralization equation, we'd have no more of that left. That was our acid invader that's changing, that's messing with the pH. We have 0.9 of this moles, and we have 1.1 moles of our acid. So all we need to do now is just come up here and plug it in. So our H plus is equal to the Ka value, 1.4 times 10 to the negative fourth. And you're like, where did you get that? Remember, we're working with the same species that we had in our original problem. Okay, 1.4 times 10 to the negative fourth. And now we're going to plug in our acid piece and our base piece. So the acid part, we have 1.1 on top divided by the base, 0.9. So then I'm going to plug that into my calculator and take the negative log of it. 1.4 times 10 to the negative fourth times 1.1 divided by 0.9, and I get that number. So that's my hydrogen ion concentration. That equals 1.71 times 10 to the negative fourth. Taking the negative log of that value, 1.71 times 10 to the negative fourth, it's going to give us our pH. And so pH is equal to negative log of my number, enter, and I get 3.77 for the pH. Remember, the pH in our previous problem was, just with the buffer, was 3.85, okay? Now our pH, when we added an acid invader, has dropped a little bit, but it hasn't dropped significantly. Like, it didn't even get to 2. So it's at 3.77. You see how the buffer resisted change in pH. Okay, I'm going to go ahead and flip over to the next page so that we have some more room with that. In B, we are adding a base invader. So we have NaOH, and in fact, we have 0.1 moles of NaOH. Now, again, Na comes from a strong base, or this is a strong base. So that means that that doesn't do anything to water. It's all about what is the hydroxide ion doing to water. So OH plus our system, okay, and it's not just water, it's actually our system. Remember, in our system, we have our hydrogen, we have our acid, and we have our conjugate. Who's going to take care of the new invader, the OH minus? You're right. This is a base, so an acid has to come in here and take care of that invader, okay? And so when we do this neutralization equation, H is going to get with OH and make water, and you have A minus left over. So you had a drop in how much acid was actually originally present, and you have an increase in the A minus. So when we put our numbers in here, we have 0.1 moles to begin with. Originally, we had 1 mole of this, and we had 1 mole of this. That's our initial concentration. So when we changed it, this went down by 0.1, down by 0.1, and this went up by 0.1. So the end of our reaction, we have none of that. We have 0.9 of our acid, and we have 1.1 of our base. So now we're going to plug that into our Ka expression, just rearranged. Ka is acid over base, so 0.9 goes on top this time, and 1.1 goes on the bottom. Okay, so I'm going to plug that into my calculator, and then we're going to take the negative log of that. So we've got our Ka value was 1.4 times 10 to the negative fourth times 0.9, I just messed that up, times 0.9 divided by 1.1. And this time, the H plus is equal to 1.15 times 10 to the negative fourth. We need to take the negative log of that, 1.15 times 10 to the negative fourth. It's going to give us our pH. And I get 3.94. Now remember, our original pH of just the buffer system was 3.85. When we added acid, our pH actually went down, didn't it? It was 3.77. When we added base, our pH went up, it was 3.94. But guys, that still didn't even change to 4. I mean, we added a lot of acid and base. That's 0.1 is quite a bit, considering we're just dropping some H pluses in there. But we've got a piece that's going to take care of that invader. And that's why a buffered system is going to resist change in pH. If you put acid in it, you've got a piece that takes care of that. If you put base in it, you've got a piece that takes care of that. Just remember, a buffered system has to have both a weak acid in its conjugate or a weak base in its conjugate. Okay, let's look and see if there is another type of problem that we want to make sure we work. Okay, so acid-base indicators, we'll come in and talk about that more tomorrow, and we'll talk more about acid-base titration. So what do you need to do for practice? Sorry about that. It's kind of all over the place. Get out of this. And so for practice, if you'll go to Echo, I think I can get there. Give it a second. There we go. Don't do it. All right, let me just go over here to Echo. And you should be able to download what you need in Echo from today's agenda. I'm going to put this video up, so you're probably accessing it from the agenda if you miss class, or you're doing some extra. Okay, so acid-base titrations, and this is actually a Google Doc that I'm sharing with you. Okay, so let's look at maybe our first problem here, and let's see if there's anything weird about it. Let's calculate the pH of a solution that contains 0.1 molar acetic acid and 0.05 molar of sodium acetate. Again, we don't care about the sodium part. So it's the acetate ion that's going to be your conjugate base. They give you the Ka value for this. So that one's pretty straightforward. Okay. Then the next part, it says calculate H plus and the percent dissociation of HF in a solution. So let's do number 2 together real quickly, just simply because we need to refresh our memories on how to do percent dissociation. They don't even want the pH on number 2. So I'm going to go ahead and write down what we have. We have we're looking for H plus, and we're looking for the percent dissociation. Okay, and we have 0.75 molar solution of HF, so there's our acid, and we have a 1.25 molar solution of NaF. Notice you recognize that Na is not going to be part of this. It's all about the F minus. And then our Ka value is 7.2 times 10 to the negative 4th. Okay, going to that page. Okay, so here's my information that I have written down. We're looking for this. We're looking for percent dissociation. Okay, so again, we're going to use our little equation. H plus is equal to Ka acid over base, or C base, conjugate base. Okay, so I'm going to plug my numbers in. I've got, excuse me, 7.2 times 10 to the negative 4th, not equals, times. My acid part is 0.75. My base part is 1.25, and that will give me my hydrogen ion concentration. Okay, so plug it in, plug it in. This is actually a pretty straightforward question. 7.2 times 10 to the negative 4th times 0.75 divided by 1.25, and I ended up with my hydrogen ion concentration being 4.32 times 10 to the negative 4th. So I've answered one of my questions. Check, I've got that. Now, percent dissociation, to refresh your memory on percent dissociation, you could look it up. But basically, I've taught you how to just do it as part divided by the whole times 100 is going to give you percent dissociation. Here's the question. What's your part and what's your whole? Well, we have to think about what acid are we talking about? We're talking about HF, okay? And they give us the Ka value for that. So that's what's going on here. We're looking at this dissociating in water. Realizing that, excuse me, your original concentration of this is 1, okay? And we're looking for the breakup. like how much did this break up? Well, to find this percent dissociation, we're going to be looking for our part, which is going to be our H plus, and this is your whole, okay? And so the part we already found was 4.32 times 10 to the negative fourth divided by the whole of 1.00 times 100. And that's going to give you your percent dissociation. So it's actually going to be kind of small, to be honest with you. If I take that number, and of course, dividing that by 1 is the same thing, times 100, and I get, wow, a really small number of percent dissociation. So 0.043% dissociated is how much. Not a lot, right? Not a lot. All right. See if there's anything else that might cause you some grief. It says write equation to show how this neutralizes. So on number 3, you've got to get rid of, you're ignoring the Na part. You're working with the other part. So you've got NaHCO3. Don't care about that because it comes from a strong base. So this is interacting with water. And then your other part was Na2CO3. We don't care about that. So we're looking at this, the -1 charge, this with a -2 charge. One of those is going to deal with an acid invader, and one of them is going to deal with the base invader. So which is which? Well, this already has an H on it, so that's going to act as the acid. So that's going to deal with the base invader. And this one is going to deal with an acid invader, okay? Remember, this is a back and forth. So if this deals with the base invader, then you have water that forms and the carbonate ion. If this is dealing with an acid invader, then you have HCO3, and that's it, okay? So you see how you've got these two reactions that pretty much are, I messed up, that's supposed to be H plus. Thank you for correcting that in your head. Okay, but you're just dealing with the two things that are conjugates of each other, and look what they form. They form their conjugates. Kind of cool, huh? All right, that one, number 4, you can figure that one out. Number 5, it says explain why a mixture formed by 100 milliliters of 0.1 molar acetic acid and 50 milliliters of NaOH will act as a buffer. That's like the second problem that I worked in this, I believe, or maybe the third one, okay, except I used a strong acid and a weak base. And then consider the acids listed in your Ka table. Which acid and its conjugate base would be the best choice for preparing a pH of 7? If you want to go back, I'm going to make sure the PowerPoint is in our agenda, but you can go back and look at that PowerPoint, and you can pick one out. Or you can look in your book, and you can find one. Okay, number 5, you're asked to prepare a pH of 4, starting with benzoic acid and sodium benzoate. What is the pH of the benzoic acid prior to adding that? That's not hard. How many grams of sodium benzoate should be added? So if you're in moles, then you can figure out grams, I think. So once you figure out the information, it says excess sodium benzoate, and you need a pH of 4. So backtrack that, get your hydrogen ion concentration from this. You've got the acid piece, you don't know the base piece. You'll need to look up the Ka value for benzoic acid. You can do that. All right, and then here is, they're saying you can use the Henderson-Hasselbalch, or you don't have to use the Henderson-Hasselbalch equation. You can just do how we practiced in class on those. It's not hard. And then it says calculate the pH. So this is just exactly what we just got through practicing on. Using that equation, H plus is equal to Ka acid over base, okay? And that's going to allow you to get your H plus and then find the pH. Now, if you had a weak base in its conjugate, then you're dealing with this. OH minus is equal to Kb, check this out, base over acid, okay? So either one of those will allow you to calculate your pH value. Just remember, if you're working with a Kb, then you're going to have to subtract from 14 once you take the negative log of that. All right, I hope that was helpful, and you've got some practice work to do so that you make sure that you have it down. I'll see you next time.